Hi, I'm Sheree McGinnis, and I'm going to kick off the presentation of JHU Team 7's final project. The competition that we decided to select for this final project was called the Lacuna Masakane Parts of Speech Classification Challenge, and it's actually a challenge that we found on Zindi rather than Kaggle. We were interested in this challenge primarily because our team members were really interested in applying NLP to a competition, and so this is what we ended up choosing. So the competition doesn't actually end for another month. It'll end on the 17th of September in 2023. And the first place prize for this competition is 3,500 US dollars. There's also a second place cash prize of 2,100 US dollars and a third place cash prize of 1,400 US dollars. As of this date, there are a total of 42 teams on the leaderboard. And we have also provided the URL for the final video. We will go ahead and consent to present this presentation after that end date of September 17th of this year. So just a quick introduction to our team. Our team is comprised of Kane, G, myself, Cherie, Chris, and Ravindra. Just a quick sharing of the agenda that we're going to go through today. We're going to start with an introduction to the competition. Then we're going to talk about the pre-processing approach. Then we're going to go into all of the modeling experiments that we've tried. Then we'll cover our latest model. And finally, we'll talk about our future work and the learnings that we've had from this competition. So just a quick introduction to the competition to start us off. First of all, the acronyms, we're only going to really use 4 acronyms within this presentation. LB is the public leaderboard, POS represents parts of speech, NLP represents natural language processing, and DNN is deep neural network. So just a quick description of the competition. The objective of the challenge that we selected is actually to create a machine learning solution that classifies 17 different parts of speech for the Luo and Setswana African languages. So we actually had to build a single solution that applies to both of these disparate languages. These languages are spoken in different geographically diverse parts of Africa. And so really kind of the main challenge that we had going into this was how do we create a single model that applies to both of these languages simultaneously? And the part of speech tagging that they're asking us to do, these 17 parts of speech that we're supposed to be tagging, that's actually a crucial step in natural language processing because it actually allows algorithms to understand the grammatical structure and the meaning of a text. So this competition is very important for us because it's going to help create the building blocks for preparing low resource African languages like Luo and Setswana for these NLP tasks. So we hope our model will be used for important understanding of these African languages in the future. Just a quick coverage of our training and testing hardware specifications. We all ended up using completely different training equipment. It was a combination of Google Colab Pro as well as Paperspace Pro and Growth accounts. So we did use a variety of hardware. Our CPUs were anywhere from 8 to 12 core. Our GPUs used anywhere from 12 to 80 gigs of memory. And our RAM was anywhere from 30 to 90 gigs. Our storage was from 15 to 50. So quite a large distribution across the board. Our competition actually did not have a time constraint for which the notebook should run within, so that gave us a lot of leeway. The dataset size, the dataset that we were provided with is comprised of 19 different training sets, and each of these training sets contains a different African language, not including, of course, the Luo and Setswana data. All right, so now I'm going to go ahead and pass it on to Chris, who's going to talk about our pre-processing approach.
Thanks, Cherie. As was mentioned, this competition aims to develop an automated mechanism to accurately predict part of speech tags for 2 African languages, Luau and Setswana. A key component to enabling this is having relevant and sufficient training data. In support of this, the competition provides training data for several African languages. This slide offers details on each of these languages. Much of the data is text taken from African news sources. It was manually labeled with part of speech tags by native speakers. The paper referenced at the bottom of this slide has more details on how this data was collected and labeled. The 2 lines on this chart with red rectangles around them are the target languages. It's important to note that this competition does not provide training data for the Luau and Setswana languages. Training data is available for 18 other African languages, but not for the target languages. This is important as our modeling experiments, which are discussed in the next portion of this presentation, are informed by this lack of training data for the target languages. Before leaving this slide, I'll briefly mention that the family and African region columns are very informative. Given the lack of training data in the target languages, selecting training data from semantically similar languages is essential. We'll discuss this more later in the presentation. Now let's zoom in on the training data itself. As can be seen from this slide, the training data has one feature, a word or token, and one target variable, the part of speech tag for that word or token. The training data is organized so that each word in a given sentence is on an individual line, and a blank line separates each sentence. Again, data is available for 18 different African languages, and all languages have the training data formatted in this manner. Now that we're familiar with the training data, let's review what pre-processing steps we'll take to get this data into a format suitable for fine-tuning a pre-trained language model. I won't go into details about the fine-tuning now, as that will be covered later in this presentation. As seen in this bulleted list, the words and their corresponding part of speech tags need to be converted into representations suitable for training using various model families. Some of the model families we experimented with are listed in the table in the lower right-hand corner of this slide. At a high level, creating tokenized input that consists of numerical values representing the class, the part of speech tag, words, padding, and separator tokens will enable the models we're experimenting with to learn from the input. This slide visually represents the pre-processing steps we briefly mentioned on the previous slide. Let's walk through the pipeline on this slide in some detail. First, the training dataset is read from one or more text files that follow the format we described earlier. In green text, I've included an actual example sentence from the Yoruba language training data. While I won't attempt to pronounce this sentence, I will mention that this sentence, translated to English, is, "What's your advice for marketers nowadays?" Once the training data has been read, it must be converted to features. 4 distinct representations are created for each sentence in the training data. First, we must convert the words in the sentence to corresponding numerical representations. A model-specific tokenizer is responsible for this conversion. It's worth mentioning that special tokens, a CLS token and a SEP token, are added before and after the words in the sentence. This is a convention used by many BERT-based models. This would look slightly different if we used another model family, for example, XLNet, but the basic concept stays the same. Once the tokens have been converted to corresponding numerical representations, we next zero pad the input IDs to the maximum sequence length. For most of our experiments, we selected a maximum sequence length of 200. Finally, the input IDs are converted to a PyTorch tensor object suitable for training. These last 2 steps, zero padding and converting to a tensor object, are common to all the produced representations, so I won't repeat them. After creating the input IDs, an attention mask is generated. The attention mask is a binary tensor that indicates the position of padded tokens so that the model does not attend to them. After generating an attention mask, a binary tensor containing segment IDs is created. In the context of a classification task, which is what our part of speech tagging task is, the class token is given a segment ID of 1, and all other tokens are assigned a segment ID of 0. This allows the model to differentiate between the class token and the word or padding tokens. Finally, after the segment IDs have been created, the last step is to create a tensor containing label IDs. The label IDs here correspond to the part of speech tags in the training data and are aligned with the word tokens. This enables the model, as part of the training, to compute the loss between its predictions and the expected part of speech tag, the label. These 4 tensors are then combined into a tensor dataset object. At this point, our pre-processing pipeline is complete and model training can begin. That covers the pre-processing approach we implemented for this competition. Now I'd like to hand it over to G to talk about modeling experiments.
Thank you, Chris. Our test data comprises words from Luo and Setswana languages, both of which are not present in the training data. The objective is to develop a single machine learning solution capable of accurately categorizing parts of speech for both languages. Essentially, our model has to be effective at generalizing across these 2 distinct languages. Several approaches were considered for building a parts of speech tagger. The initial approach involves adopting a supervised learning technique, and this entails training a machine learning classifier, such as using logistic regression, random forest, or SVM, and using word embeddings as the foundational features. Alternatively, we have the option to use pre-trained NLP models that have already undergone extensive training on African languages that are available from Hugging Face's Transformer library. These pre-trained models can be fine-tuned for downstream tasks like part-of-speech identification. Our experimentation encompassed both methods, revealing that using pre-trained NLP models yielded better performance. The subsequent decision in our design process was centered around the choice of the source language for training our model. This decision held significant importance due to the absence of any training data for the languages under prediction. Selecting a source language that is linguistically similar to the target language is important since similar languages share certain syntactic, grammatical, and vocabulary characteristics, making it easier for the model to generalize. Another aspect we considered was that languages spoken in neighboring regions might exhibit comparable linguistic traits, thereby aiding in knowledge transfer. Another factor of consideration pertained to whether using a single source language or multiple source languages is more advantageous when training a model for a target language without annotated data. Using several source languages can create a bigger, more abundant collection of language knowledge and has the potential to enhance the model's ability to generalize. Training across diverse languages can enable the model to better handle unfamiliar languages by recognizing linguistic commonalities and adapting to new languages. However, it's worth noting that training on multiple languages might also introduce interference between the languages, thereby impacting the model's performance, which is what we saw with our experiment. The model showed best performance using one or two languages. During our exploration of multiple source languages, we needed to decide whether to employ one single model for all these languages or to have separate models for each language. A single model can learn shared linguistic representations across languages, potentially improving generalization. On the other hand, having separate models has its own advantage in that each one can be fine-tuned for the unique features of its respective language. Additionally, we also experimented with creating an ensemble model, and this involved combining predictions from individual models for each language using a method called majority voting. The idea behind this was that each model could bring its own distinct perspective, and by combining them, we could notably increase the accuracy and dependability of the model. Fine-tuning the hyperparameters was a crucial phase for optimizing our model's performance. We've investigated several hyperparameters, including the learning rate. This determines how big of a step the model takes to adjust its parameters as it undergoes training. It guides the speed of convergence towards a solution. If set too high, training might not converge. If too low, training could be sluggish or stuck in a suboptimal state. An epoch signifies the complete cycle through the entire training data during model training. Having too few epochs could result in underfitting, indicating the model hasn't learned enough from the data. Too many epochs might lead to overfitting, where the model becomes too attuned to the training data and doesn't perform well on new data. The batch size refers to the number of training examples or data points that are processed together before updating the model's parameters. Opting for a larger batch size comes with certain advantages, such as better parallel processing on GPUs, potentially quicker training times, and steadier adjustments to model parameters. However, we've also observed that larger batch sizes necessitate increased memory and computational resources. The max sequence length corresponds to the utmost length of the sequence that the model is trained on. If the input sequence surpasses this length, they'll be truncated, and if they're shorter, they'll be padded. Lengthier sequences demand more memory and computation time. In addition to these hyperparameters, we also tested weight decay, which is a regularization technique to prevent overfitting. Warm-up steps, a technique used to gradually increase the learning rate during early iterations, and atom epsilon, a small constant value which is used to ensure numeric stability during optimization and mitigate potential issues with small or zero gradient values. All of these hyperparameters were tuned while aiming to strike a balance between training duration, memory utilization, and GPU consumption. And more is not necessarily better, especially with accuracy and the number of epochs and batch size. Some other experiments we've undertaken were to formulate an error analysis. This involved calculating the distribution of predicted parts of speech tags and contrasting it with the distribution of parts of speech tags present in the training data. And the goal was to discern patterns and errors and make adjustments for future experiments. Additionally, the technique of zero-shot transfer learning was employed to generate predictions for parts of speech tags. Zero-shot transfer learning takes advantage of the shared linguistic properties and structures among languages to make informed predictions, even though the model hasn't been explicitly trained on a target language. And this concludes the portion on modeling experiments. I'd like to hand it over to Kane to talk about the latest model.
Thanks, G. Let's start by reviewing our team's performance in the Zindi competition. The metric that the competition used to score our entries was accuracy. As you can see, over the 6-week period, we continued to make entries in the competition with slowly improving leaderboard score. However, we failed to improve our leaderboard rank any of the weeks. Our latest high-scoring entry utilizes a pre-trained model, AfroXLMR. This model is pre-trained on 17 African languages as well as 3 high-resource languages, Arabic, French, and English. We then further trained this model with part-of-speech training data from the Yoruba language. And finally, we focused our efforts on optimizing the model's hyperparameters you can see below. The main challenges that we faced while developing this model were number 1, the notebook runtimes. Because of the large size of the AfroXLMR model, we were not able to train it on standard hardware. We resorted to using smaller versions of the model, base and small, to perform our optimizations that we could then transfer to the large model. The second challenge was that there's no ground truth for the target languages. Because we had no labeled data for the 2 languages we targeted, we were not able to effectively gauge our performance without submitting the predictions to the competition. Because of that, we tried to use what techniques we could to get a sense of how the model was training. We utilized TensorBoard to visualize the training loss over the steps. We also charted out our predictions by category to see how they stacked up against the other African languages. As you can see in the second set of columns from the right, without post-processing, we noticed that there were some punctuation and number parts of speech that weren't being classified correctly. We then implemented a post-processing routine to handle some of these misclassifications. As mentioned earlier, our latest model is based around the AfroXLMR family of language models. AfroXLMR is a version of XLM Roberta, which is pre-trained via the masked language modeling approach on the previously mentioned 17 African languages and 3 high-resource languages. XLM Roberta, in turn, is a multilingual version of Roberta, with Roberta, in turn, being an optimized and pre-trained version of the popular NLP model, BERT. BERT is a common model used for various NLP tasks, including text classification, named entry recognition, and more. One of the core power features of BERT is its masked language model style of training. The core concept of this you can see on the right, where a sentence is passed in with one of the words masked off. The model is then able to use not only the words that come before the masked word, but the ones after as well to make the prediction. This is in part where BERT gets its namesake, in that it is able to look in both directions of the unknown word for context. The remainder of our model is structured very similarly to ones that we have covered in class. First, we would take our training data and split it into batches. At this point, we would also run a function to zero any lingering gradients from previous steps. Then, we set up our loops to run through the given number of epochs and steps. Within those nested loops is where we perform our training. First, we pass a sentence as an input into the model. This will calculate a loss. Then we use the loss.backward function to backpropagate this loss and collect our gradients. Finally, we'll use the optimizer step function to adjust our model parameters based on the previously calculated gradients. And then finally, we reset the gradients to 0 again, so that they don't carry over to the next step. Once we've trained the model with our chosen language, then we can make our predictions. To do that, we need to take our test data from the competition and tokenize the words. Then, one word at a time, we'll pass it back into the model to create our prediction. Finally, we utilize our post-processing step to comb through and find any misclassifications on known entries like punctuation and numbers. Now, I'd like to hand it over to Ravindra to wrap it up with a conclusion.
Thanks, Kane. My name is Ravindra, and I will be talking about future experiments. Traditional multilingual models like XLM Roberta and BERT, although they work very well for well-known languages like English, French, and German, They do not generalize well for languages which are low on resources, like Lao and Setswana language, or the languages which they haven't seen during the training. So we were looking for a framework which can adapt to the unseen language. We researched Maddox framework, which is an adapter-based framework that enables high portability and parameter-efficient transfer to arbitrary tasks and languages by learning modular language and task representations. Here is how it works. So let's consider an example wherein we have a source language which is Zulu and a target language where we need to predict pause tags for a Lao language. Okay. So here what we do is there are two adapters in this framework. One is a language adapter and other one is a pause task adapter. Okay. So what we do is we start with an unlabeled data set of a source language which is Zulu, and we just train a source language adapter part of the framework using this unlabeled dataset of the Zulu language, right? So this dataset just contains sentences of news articles. It does not have any labels. Okay. So then what we do is we take the unlabeled dataset of the target language, which in this case happens to be Lao, which is again the news articles from that language. It's an unsupervised dataset. It doesn't have any labels. And we train a second language adapter, which is called a target language adapter. And we train that adapter using just this unlabeled dataset. So this adapter is very good at recognizing the language itself. Okay, so we train two language adapters. One is the source language adapter and the second is the target language adapter. Then what we do is we train a second type adapter, which is called a task adapter, and task in this particular case happens to be a part of the speech tag. So we train that task adapter using the part of the speech tag from the source language, which happens to be Zulu language. So where we have words in the Zulu language as feature and the part of the speech tag for those particular words as a labels, right? So we train the task adapter, which is a supervised model training, and we train this task adapter using the supervised dataset. So we train the models which contains all three adapters, one source language adapter, one is a target language adapter, and the one is a pause task adapter. And then we store the model. And this concludes the training of the model. So during the inference part, what we do is we swap the language adapter in the model by the target language adapter, and then we ask model to perform the inference for the pause tags. So we keep the pause task adapter as it is, but we swap the language adapter from Zulu to Lao language, and then we ask model to perform the inference. And this combination performs better than just using a simple fine-tuned language model just on one language. So here are some of the references from the media that we used to study part of the speech tagging, as well as the models from Hugging Face and basic concepts behind the pause tags. This brings us to the end of our presentation. Thank you very much.